We're going to take a look at doubling time and half-life with exponential models. We're first looking at the half-life. So we're given that the half-life for Rocephin is 4.6 hours. We're asked to find the hourly decay factor. So I'm going to base my beginning for finding this on this idea of half-life. We know that half-life is the amount for it to decrease by half. So that would mean that we would figure out 1 minus 0.5, which is that 50%. So that means that we have 50% remaining. However, the exponent on that 50% is not 1 because that happens over 4.6 hours, and we want to go to hourly. So hourly is a shorter time frame, so we're going to use a fractions. We're going to take the half that remains and use an exponent of 1 over 4.6 to figure out how much would remain after 1 hour. So I'll put this on my calculator. When I put that on my calculator, make sure you're using parentheses around that exponent. And rounding off, I get 0.86. So that is the hourly decay factor. Now, the second question. How long will it take for only 1/4 of the Rocephin to remain in the patient? So we know that over the course of 4.6 hours, the amount of Rocephin goes down to 50%. To half. And then over the next 4.6 hours, it's going to go to half again. So that means we would have 1/2 of the 1/2 that was there. And so if we multiply those, we would end up with having 1/4. And so our amount of time, well, it took us 4.6 hours to get to half, and then another 4.6 hours to get to half of that. So that would be a total of 9.2 hours to get to the 1/4. Now, there's another way of looking at that as well. We have our general concept of an exponential equation, and we figured out the hourly decay factor is that 0.86. So we want this to get down to 1/4. So I'm going to put that in for my n, and I'm going to put that in as a decimal to 0.25. That would be how much was left if we were starting with an amount of 1. And so we have 0.86 t. So in order to solve this, I go to my graphing calculator. This part becomes my y1. So y1 equals 0.25. And this part becomes my y2. And so I go to graph that. So on my equation, I already know the answer is 9.2 hours. So I'm going to put my x-axis from 0 to 10 in my window. And I'm going to put my y-axis from 0 to 1 because we had 1 as our starting amount. So the first equation I graphed is the 0.25. So that comes across as a straight line. Sorry, my line's a little crooked there. So that's the 0.25. And the second thing that we graphed is this exponential, and it is exponential decay. So that's going to come down as the nice curve, and they meet right out about here. And then I do second trace, and I find this ordered pair right here. And I get that ordered pair, and rounding off, that is 9.2, comma, 0.25. And so from that ordered pair, I also have this, that it is going to take 9.2 hours for it to be at 1/4. Let's take a look at a doubling time example. So we're given that the doubling time for community-acquired MRSA, that's that medical resistant staphylococcus, so is 30 minutes. Find the hourly growth factor. So this concept of doubling time. So it starts out at 1, because everything starts at 1, and then if it doubles, it has 100% growth. So that means we would be at 2. But that 2 is not hourly. That 2 happens in 30 minutes. Okay? So it doubles. It goes from 1 to 2 in 30 minutes. And we're supposed to get hourly. Hourly is now bigger. When it's bigger, we're going to use an exponent, not 1 over, just the exponent. So 30 minutes, there are two 30-minute blocks in an hour. So I'm going to use an exponent of 2, and we all know 2 squared is 4. So our hourly growth factor, 4. Now it asks us, how long will it take for the number of MRSA cells to triple? I'm going to go to my general equation. So n equals the starting amount, the a factor, exponent t. Triple, that's 3 times. So n is going to be 3. Starting amount, 3 is 3 times what? Well, it's 3 times 1, so starting amount of 1. My a value, that growth factor we found is 4. And then we have t as our exponent. And so then I'm going to go to my graphing calculator. I'm going to make this my y1. I'm going to make this my y2. And I'm going to go to my graph and graph them. So here's my graph. I went 0 to 5. So 0 to 5 hours, because I know that it doubles in 30 minutes, so it's not going to take it long to triple. And I went 0 to 5 in this direction. Truly my biggest amount here that I care about is 3, but I want to be a little above 3. So the first thing that graphs is that 3, so that's a straight line. And the next thing that graphs is this growth equation, and this one comes up pretty quickly, like that. And then I find this point where these guys meet, so right in here, and that is 0.79, comma, 3. So what does that mean? That means that in 0.79 hours, the number of MRSA cells are going to triple. Kind of scary. Honestly, that time frame is for in the lab, not in a human body, but it's kind of scary in the human body as well. So hopefully that helps you think through the concepts of half-life and doubling time. Key is that when I'm finding this hourly growth factor, doubling brings in this 2 from 1 plus 100%. And on the previous slide, we brought in this 0.5 from 1 minus 50%. And so those help us to find the hourly growth or decay factors. And then the other concepts we have used in other problems as well.